you won't remember a lot, and with time, it will vanish into thin air, as I always tell students. Okay, so guys, let's have a short break, and we'll be back in 5 minutes to complete the last part. Okay, so let's have a five-minute break. So now we move to the case where we have convolutional networks for two-dimensional inputs, which means the input is actually an image. So in this example, we see that we have our input X, and it's a two-dimensional matrix. And we apply a kernel, and the kernel right here is a 3x3 kernel. So this is our kernel omega, we call it over here, okay? And the idea is actually the same, so it's not too difficult. So you apply this kernel to the input pixel. So if we just draw this quickly, and I'm going to just draw it in this way just for the sake of simplicity. And every time you apply this, you basically create a weighted sum of element-wise multiplication. That's a convolution. You sum all the outputs after doing the element-wise multiplication. So that's the summation over here, and it gets you the output, and the output is actually this value over there, which is H2 okay? So by doing this, by sweeping or this kernel along all the image values or pixels, you end up with filling out all of these values inside. Now, what happens, for example, this happens when we take this the bottom square in the image. So this allows us to generate the value H35. So you guys see it here, H35. So when we take this square in the top part of the image, that generates H23, okay? So this is the hidden layer that we are creating by this two-dimensional convolution. Now, what you guys notice that if we go over this image, right, we won't be able to have all the values inside. So we're going to have a small kind of, values predicted in the output hidden layer. So to change that, of course, we need to do some padding. So for the edge, for example, elements over here, we do a padding of 0. So 1 padding, and that allows us to predict or get the value of H31. Okay, so you can see it there, the element there. And when we do the padding of this element, right, so we get the value H16. And the padding will be actually applied to the whole image. So we will immerse the image in a bunch of zeros from all sides, from the 4 sides, okay? So now to calculate the output, so let's say C0. So there's a formula. The formula is also very simple. To calculate C0 output channels, we need basically F times F, that's the size of the kernel, and Ci is the size of the input channel times C0 weights to calculate. So we need, this is a huge high dimensional tensor, a lot of values to learn and the inputs to store also. And we have C0 biases, and C0 is the number of the output channels. So we have a bias for every single output channel. We will have a bias to learn, okay? So you guys can see now, as we moved from one-dimensional convolution to two-dimensional convolutions, we have a very high-dimensional problem to solve, and the number of weights has exploded. So these are all the number of weights that we need to actually store along with the biases, all right? So now let's look at this example, another simple example. So this is, where we have an input RGB image. So this is a colored image. It's not, binary image. So we have 3 channels. So the input data has 3 channels. So to perform what we call convolutions, it's actually a simple task. So we take this, weight and we multiply it by each cube. So now we're doing a I would say three-dimensional convolution, but I think about it as we have these the three dimensions here are channels. So however, we learn a weight for each channel. So as we do that, we can see that we can easily map the center pixel into an output over there by taking this over the whole, like sweeping this over the whole input image tensor. Okay, so this will give us one channel, one input, one output channel. So this is one channel, and the value here is simply convolving these two, basically one by one. So we take the first and we convolve it by this, first weight, etc. So we can do it in this way. And then we do the summation, and as we sum over all of these, you get the final output over there. You add, of course, you need to add the bias beta, and you apply the activation. So we have the activation over here, and that's how we get the value inside this hidden layer. So if we want to add more kernels, we can add more kernels. So we add a second kernel here. We do the same type of, convolution, and we do the same type of multiplication and then summation. So this is our convolution operation, and this will allow us to get a second, channel over here. So this is, channel 2 that we have produced, and it's related, or it's, produced by the second kernel that we have over here. So we can call this, for example, omega 1, and this is omega 2. So we multiply kernels and add output channels, and this is, the key operation that we perform when we have RGB images. So it's actually quite simple. And now we're going to talk about two important points here, which is, downsampling and upsampling. So downsampling is basically, these are two operations that we use often in convolutional neural networks, okay? So we have the downsampling operation and we have the upsampling. So the downsampling, as we have seen, that if we use a stride of, 2 or higher, larger than 2, okay? So then we will end up basically with a sort of a downsampling or scaling down the size of the input, okay? So there are different downsampling techniques, and let's explore them here together. So the first one is what we call subsampling, okay? So first, what do we have? We have an image. This is the input data, okay? And it is 4 by 4. That's the size of our input. It's 4 by 4. So here we will apply a 2 by 2 sampling. So 2 by 2 means we're going to look at each 2 individually. So the first, 2 by 2 quadrant, second 2 by 2, third, and 4. So we have 4 quadrants here. And every time we're going to apply a particular downsampling technique. So in the first technique, we do what we call subsampling. So we retain every other input. So here you do skip and you retain in each one. So in the first quadrant, in the second one, and this is, you end up with these 4 values that are stored in the output channel. Okay, so this is the output channel of the 2 by 2 subsampling. Now for the for B, 2 by 2 max pooling is actually also quite easy. So basically you look at each quadrant and you take the maximum value. So the maximum value here is 6. Then the maximum value in the second quadrant, so you look at 2 by 2, of course, so 8. And then you have 8 here and you have 4 there. And by picking the maximum value within each quadrant, you get your pooled unit or your pooled value, and this is the output. So the output, we went from a 4 by 4 to a 2 by 2. So we divided basically 4 by the size of the pooling, and we got 2 over there, okay? So now the mean pooling is also a different kind of pooling. So we don't take the max. So remember, guys, these operations, they will be inputted to an activation function. So the activation function, right, here is, it's, we can do pooling, and then we can do another type of activation. And if we do a sort of, apply an activation function, so you need to keep in mind that in max pooling, I retain the highest or the strongest signal, But in mean pooling, I retain the average signal within a quadrant. So I look at the average and not, so this regularizes more the signal. So we're not looking at peaks. So the activation may be very high here because we are increasing the value. So the neuron may get highly activated because of these values if we apply activation immediately. But for the average, we're kind of somehow toning down the activation, the follow-up activation, if we have a follow-up activation, okay? So let's look at mean pooling. So mean pooling is also quite simple. So you take these, the average of each quadrant. So the average of these numbers is 3. The second one is 4. This one is 5. And then the fourth quadrant is 2. All right. So that's quite easy. So downsampling, of course, is important because remember, guys, you want to shrink your network. You're having, for example, as here, let's go back to this nice example here. So we have 40 values as inputs, and we want to end up with only 10. So somehow we need to down scale the network or downsize the network in such a way that I'm transforming 40 inputs into 10 outputs, right? So downsampling or downscaling is a very important operation, especially if you're doing supervised learning tasks such as, classification, right? If you're doing regression, okay? So you want to end up maybe with a single score or multiple scores to predict. So y1 to yn, etc. So we have seen multilinear regression, different types of regressions in the first lecture. And yeah, so now on the other hand, the opposite operation or the I would say, like, it's not completely opposing. It's not in terms of mathematical formalization, right? But if we think about it as an opposite of the opposite of downsampling will be upsampling. Okay, so you're scaling up the image. So scaling up the image, why would you want to scale up the image first? So let me give you an example before we go into these operations. So first you have an image, and let's say this is an image of a, so we have seen this example before. So this is an image of a tree. And what you want actually to segment the tree. So segmenting the tree means coloring it, okay? So I'm gonna color all pixels here and label them as class, for example. This is class 1, and the rest will be 0, okay? So this is semantic segmentation. So semantic segmentation, it means that if I have a 28 by 28 image as input, I need to have 28 by 28 output. So how are you going to design that? Somehow, you may think about it, okay, so I'm going to do convolution neural networks here. I'm going to vectorize my image, and then I need to find exactly, if you vectorize, so if you do it in 1D convolution, so let me duplicate that, sorry guys. All right, so here we're doing 1D convolutions just for the sake of simplicity, but you can do 2D, okay? So you need to think about what I'm going to build here. So in this example, you may think, okay, so maybe I can just, use the same size. So I can learn different layers and I can preserve the same size as in one convolutions with padding and stuff like that. And I learn multiple, H1, H2, and then I have the final image here. But this doesn't make sense because you're not reducing the dimensionality of your data. Why this doesn't make sense? Because first, you have many pixels that are irrelevant, okay? So here you have irrelevant information in the input data. So you don't want to retain the same dimension. You need to somehow decrease the dimension, okay? So you need to decrease the dimension to, learn what is relevant. Okay, relevant, it means what allows me to find a tree or to recognize a tree. So somehow this is a very bad solution. So what you need to do is to somehow in the first early layers, you need to kind of maybe use different strides, and you need to downsample. So as you downsample here, you reduce the size of the image. So you went from n, like from a big image to a very small image. So the problem is like your output is of the same size as the input. So how are you going to kind of fix this? So the idea is to do, to implement the opposite operations. So here you do what we call upsampling, okay, or upscaling. And from these guys, you regenerate the original size. And this is what we call actually an encoder network, encoder part. And this is the decoder part. Okay, so the encoder is a downsampler, and the encoder is a downsampler, and the decoder is an upsampler. So now let's look at the upsampling operation, which is important for generative, generative learning, where you're generating data from data, especially images from images, for example, or videos from videos. So first we have what we call the first upsampling technique. Is very simple and naive. It's called duplication. So duplication, it means you duplicate the same value. So I want to go from a matrix. So I set the size of my output. So I need to get a 4x4, or I need to get a 6x6, okay? So if I want to get a 4x4, I will create my 4, quadrants right here. And in every single quadrant, I'm gonna duplicate the same value. So here I put a bunch of 2s, 4s, etc. And here I'm going to select different values. So here 4s and 8, okay? So the second example is what we call max unpooling. This is the reverse kind of operation of pooling, okay, or max pooling. So max unpooling, it means you redistribute the values to their original positions. So let's say, if you guys remember, when we did the max pooling here, we had these values, but we need to figure out where did we take them from. So in this example, we need to kind of, trace them back and put them back in their original positions. Okay, so I know that the 2 was taken from this position, the 4 from this one, this 4 was taken from this position, and this 8 was taken from that position. So I put them back into their quadrants, okay? And I set the rest to 0. So everybody else will be set to 0. So this is what we call max unpooling, all right? And the last one is a bilinear interpolation. So basically what we do, we spread these out, the values, we spread them out, and we bilinearly interpret them. So spreading out, let's do different colors so you guys can see. So here, and then you do, kind of a bilinear interpolation with some padding over there. And you can see that this value 3 is, 4 plus 2 divided by 2. This 3 also is 4 by 2 divided by 2. So you take, the neighbors and you do a bilinear interpolation. And this is another way of filling in the values inside the 4x4 upsampled version of this 2x2 matrix, okay? Cool, so these are, different techniques for downsampling and upsampling, and we understand when we actually need to use them. But downsampling is I would say, we need to downsample all the time, because whether you're doing, like regression, any kind of supervised SL, supervised learning or unsupervised learning, or you want to do, for example, generative learning, you need to downsample because you need to learn a compact representation. This representation is a low dimensional representation that is a compressed signal that allows us to represent the original data very accurately, okay? So downsampling is an important step in all neural networks, I would say, okay? Upsampling, you need it when you need to kind of reconstruct the same size of the data, and that's when you upsample or you try to kind of decode. So if you don't want to kind of shrink it to only a few values or a few labels or a few scores, and you need to reconstruct, so you need to do some upsampling, and this is particularly important in generative learning or segmentation tasks, image segmentation, image labeling, etc., and image generation too. All right, so now let's look at another example. So we're gonna wrap up with these two. So basically, the first one is, you know, what happens when we change the number of channels. And we're gonna look at, you know, transposed convolution in 1D. So transposed convolution is allows us also to do a sort of upsampling. Okay, so upscaling. And then we will look at one-by-one convolution and how we can collapse different channels into a single output, okay? So first, let's start with the transposed convolution. So in this example, we have the color indicates, of course, the same shared weights. So we have our input data, and we have a kernel, a three-dimensional kernel. We use a stride of 2. We have also here, we don't use, you know, like, we use a padding. It should be of, because we're using the first one, actually it should be padding of 1. I always have issues with padding. Okay, so 1, because there is a 0 over there that's not shown, okay? So in this example, what we're doing, we're using a single, like this is a regular example where we're having our you know, convolution in 1D. So this is a simple convolution in 1D. So what I would like you guys to think about, the transposed convolution. So in the immediate convolution, you go from X to H, and then from the transposed convolution, you actually have a lower number of input channels and you want to reconstruct a higher number of output channels, okay? So the way you think about it is of taking this matrix simply and transposing it. You simply transpose the matrix, and by transposing the matrix and applying the matrix, apply it to, you know, like the input X, you will be able to reconstruct all these, you know, kind of values. So the transposed convolution, for each input, basically, it contributes 3 values to the output layer with twice the size of the input layer. So let's look at that mathematically, so you'll understand it better through this example. So I found this in a tutorial, and I'm gonna put it in the caption below the video. So in this tutorial, what we have, let's say we have an input size of 2 by 2, okay? And we want to do here we're doing a transposed convolution of stride 2, and this is the kernel. So the idea, basically, in a transposed convolutional layer, the input is a feature map of size IH by IW. So this is the input, okay? Where IH and IW are the height and width of the input. So let's say this is the input channel. And we have a kernel size. This is a very generic formula. Kernel size, here it could be asymmetric, but usually it is symmetric. So KH by KW, where KH and KW are height and width of the kernel. Now, if this stride here, if this stride shape is SH and SW, which means this is, you know, how the horizontal and the vertical, strides, okay? And we have a padding of P. The stride of the transposed convolutional layer determines the step size for the input indices P and Q. Okay, so here we can easily calculate the output of this transposed convolution, a layer which will be calculated using this formula, and you guys can play with it and can see whether it kind of makes sense to you or not. So these are the formula of what we call, you know, the upsampling using the transposed convolution. Okay, so how does it work? It's kind of simple. So basically, you take the input, and what you do is something very different. You slide the input over the output, okay? So you're doing the opposite of what we have done before. So usually we slide the kernel over the input. Now we slide the input over the kernel, and this is what it is. Why is it called transpose? So you're doing it the other way around, and here you take this value, okay? So you multiply this whole kernel by this value, so you get a bunch of zeros over there. And then in the second convolution, you multiply this whole kernel by the first value of, the second value in the input, you're gonna get this quadrant. And then you multiply it by 2 here, okay? So you're gonna get 2, 8, 4, 6, right? And then the last one is you multiply it by 3, the third element. And by multiplying the kernel by this third element of the input, you get this quadrant over there. And then you're doing a summation. Basically, this is the output of the transposed convolution. So it's actually pretty simple, and it allows you to, change the size of the input from, you guys can see 2 by 2 to a 4 by 4. So we upscaled. All right, cool. Now, that's, for the transposed convolution. Now, a last point here we're going to cover is once you have a layer H, okay, so this is our layer H. It has, height, width, and these are the number of channels. So we have the green channel, which is one kernel. We have, the pink channel. We have the blue channel, etc. So we have multiple channels. All right. Now, how can we collapse all these channels into a single one? Okay, so we want to get this size. We want to get, width times height, and we collapse all of these. So basically here it's very simple. We use what we call a one-dimensional kernel over here. So to change the number of channels without spatial padding, we apply a 1-by-1 kernel. Okay, padding here. So what is this 1-by-1 kernel does? What does it do? So we take this basically, and you think about it, every time we're going to sum along channels and add the bias. Okay, so we create a weighted sum along these channels. So we take the values in this kernel, we multiply each element in this vector with these values, we do a convolution basically, and then we add the bias and activation, and then we get the value over there. So for this one, we get over there. So once we sweep over all of this, all of these elements inside, right? So all of them, we're gonna get these values. So it's actually very easy. So think about it this way. Every time I am applying a convolution, so let me choose a different color. So I'm applying a convolution here, right? And I'm, basically I'm collapsing all elements because I'm convolving and I'm summing, right? And I'm collapsing all this row into a single value over here. Okay, so all of this collapses into a single value. This one also, we have a weighted convolution. We multiply and we do a summation, then we apply activation, add bias, of course, apply activation, and we're gonna get this value over there, okay, in the hidden output layer H prime. So that's quite simple. If you want to add another channel, so instead of having, for example, 10, you want to end up with 2, you can easily add another convolutional, one-dimensional convolution here. And this allows you to collapse these differently, and you can change and play with the number of channels. You can end up with having 2 channels over there. So it's actually a very simple operation, and it allows you to play with that. And I think knowing these tricks is important, because it will help you in designing, networks in a very, I would say, task-oriented way, depending on your target learning task, okay? Cool. So now the last part we're going to cover here quickly, samples of CNN architectures and learning tasks. And in this example, we will see 3 different fundamental, I would say, or early, very early convolutional neural networks models. So in this example here, we first start with AlexNet. So AlexNet was originally designed for image classification. So it was trained on the ImageNet, which has 1.2 million training samples, 50K validation samples, 100,000 testing samples, and 1,000 classes. So it's a huge data set. And AlexNet, which has this architecture right here, right? It's a simple architecture, was trained to solve this, this complex classification problem. So AlexNet basically takes in this ImageNet data, which has a size of 224 by 224. You can see it is composed of simple, convolutions, stride 4, different strides, max pooling, You have convolutional, a convolution again, 5 by 5, another max pooling, convolution 3 by 3, max pooling plus a fully connected layer that we added here. So 3 fully connected layers and a softmax where we output the 1,000 classes that we want, probabilities that we want to predict, okay? So it's a simple network, it's not too deep. And you guys can actually verify the input and the output dimensions here by applying the formula that we have seen earlier, okay? So AlexNet here, it inputs at 200, as I mentioned, 224 by 224 image, outputs 1,000 dimensional vector representing class probabilities. So the network first convolves with 100 by 100 kernels, stride 4, creating 96 channels. Okay, and then it decreases the resolution again using max pooling. So max pooling decreases the resolution, applies, 5 by 5 convolutional layer, another max pooling, followed by these, so this is what I explained earlier, and then you have the final layer over there. So it's actually very simple, a very simple network that led to some good results. However, this network has a lot of parameters. It has 60 million parameters, okay? So to be able to train an AlexNet, you need to kind of estimate 60 million parameters, which is not really affordable. You need to have the right resources to train an AlexNet, okay? Now, the next model is a more complex model, I would say, which is a VGGNet, okay? So the VGGNet was originally designed for object detection. And object detection, let's look at this example. So it was used on the YOLO object detection data set. So the input image is reshaped to 448 by 448 and divided into regular 7 by 7 grid, okay? So it's a 7 by 7 grids. Here you divide the image into what we call super pixels, okay? 4, 5, 6, 7. So these are super pixels. And then the system predicts the most likely class at each grid cell. So here it tells you that it colors them based on the object. So basically the orange here will be is the car label. So it means that there is a car over there in this area, which is, you can see here. So the other colors, will detect different objects. So there is a dog. So the blue means a dog. You can see here the blue is a dog, okay? And then other colors will denote other labels. So this is how they're doing the object detection. So they are detecting objects. So detecting a bicycle here, detecting a dog here, detecting a car over there. And this is an object detection problem, okay? So during the inference, the most confidence value, during the inference, the most likely bounding boxes are retained, and boxes with lower confidence values that belong to the same object are suppressed, okay? So you can see here in this detection task, you have so many bounding boxes. A few of them are thin, many of them are thin, and a few of them are actually thick. So what the model is doing is taking the boxes with the highest confidence and retaining those to do the detection of the objects, okay? So this is how the model works. And now let's look at the architecture so you guys can read the original paper on the VGGNet. So it's actually at the same scale, I would say, as the AlexNet. It's a heavy network to train. And it has all these kind of operations, so convolution, max pooling. You have different operations. You're kind of, concatenating or stacking, and then fully connected layers to get a softmax and detect the 1,000 objects over there, okay? So the network outputs 1,000 activations corresponding to the class labels that are passed through the softmax to create the class probabilities over here, okay? So that's the VGG net, and this is another example. So you can see that this network has been trained on the YOLO data set, which in the testing stage, actually, we didn't have it wasn't trained on paintings, okay? So the object detection system works well even on paintings that are quite different in style from the training corpus. So the training corpus didn't have any kind of paintings, and you can see here that the network performed very well on images from kind of different distributions, which are painted images, and it was able to generalize quite well. Okay, so you have the detection of the objects. For example, here it recognizes that there is a horse. So the horse is in the within this box, inside this box, and the person is inside this box. There are two actually in the image, and it's kind of nicely detecting them. Okay, cool. So the last example is an semantic segmentation learning task with an adapted version by No et al. In 2015. The paper was published in 2015, and this is the adapted version. So as you guys can see, you know, like up to here, we have a simple VGG net, okay? Then what we do, we kind of, you know, transpose that. So here we got, you know, like a sort of, you know, like learned representations down there, and we needed to do some upscaling, okay? So here, this is, as I mentioned earlier, this is a decoder part of the network, and this is the encoder part where it encodes the original data into a low dimensional space. And then from this low dimensional space, we can reconstruct the original, we can reconstruct the target image, which is a segmentation here of the original input image, okay? So in this task, we need to do some, they call it deconvolution, but some people don't like the word deconvolution. They call it transposed convolution with max unpooling, and all these upsampling operations, they lead to a final layer where we do some convolution here in softmax to get the probability for each pixel to label them, you know, like using a particular class label, okay? So yeah, so that's pretty much it. This is the VGG adapted network for, you know, image segmentation. And you can see these are very nice examples. So we have the input image. This is the input image. This is the ground truth. And we have the result. And you can see that for completely different images, the network is able to identify and learn that there are multiple objects. So it recognizes the class car with gray color, person here with kind of, you know, salmon color, and you have green for a cow over there. So, and horses is like, you know, pink. So these are the colors of the classes, and the algorithm or the deep learning network is able to detect those. So the only drawback is that, you know, after a certain depth, because all these networks are actually kind of, they have multiple layers, many convolutions, especially the image segmentation one. After a certain depth, the network becomes harder to train. So it kind of, you know, it's difficult to train these deep networks. And there are so many reasons for that. And we're going to discover those in the next lecture, in the next session, and see why these networks struggle to converge, to be well trained, and how can we solve, you know, these challenges or hurdles in training such deep networks. Okay, cool.